Hi everybody, welcome back to Synthetic Biology 1. Today we're going to discuss a super practical laboratory skill, working with units of concentration. Biologists express concentration in a variety of different ways. You will often have to convert between different units of concentration when you're working on your own recipes and protocols. In fact, you'll do it so much that you will wish that scientists could just get their act together and agree to express concentration in just one standard way. But they won't. So you give up on that dream and you learn to convert like the rest of us. Number 1, percent volume by volume. This notation makes the most sense when you're mixing liquids in roughly equal proportions. To make a 10% glycerol solution, I take 10 mils of glycerol and then I add water to a total volume of 100 mils. A common mistake is to think that this means adding 100 mils of water. But 100 mils refers to the total volume, not the volume of water. In fact, you'll be adding around 90 mils of water to 10 mils of glycerol to get the final solution. I say around 90 mils because I don't know the actual exact number. Because of the magic of mixing, when you mix two different liquids, the total volume is not always equal to the sum of the separate volumes. Only chemists really understand why this is. We're biologists, so we won't worry about it. But the important thing is that when you prepare your solution, you keep an eye on the final volume. You start with 10 mils of glycerol, then you add water until the whole thing has a volume of 100 mils. Number 2, percent weight by volume. This notation is used when we're adding a dry powder to water. It might seem weird to calculate a percent as a weight divided by a volume. Normally, we think of percentage as a unitless number, meaning we should be dividing two things with the same units. The convention makes a little bit more sense if you consider that 1 milliliter of water weighs exactly 1 gram. In biology, almost all of our solutions are water solutions, so you can think of volume and weight as being interchangeable. Just like last time, remember that the volume is the total volume, not the added volume. Number 3, grams per liter. Good. An easy one. You take this many grams and you dissolve it in that many liters. Number 4, molarity. Molarity is a measure of the total number of molecules of a substance. It's useful when we care about the total number of molecules and not how much those molecules weigh. To determine how many moles you're adding, you take the weight and you divide it by the molar mass. Grams divided by grams per mole equals moles. Number 5, not quite molarity. 1 mole is a lot of molecules and 1 liter is a lot of water. Often in biology, we don't want to think about quantities that large, so we cut down molarity into tiny little bite-sized units. An example of this that I see a lot is picomoles per microliter. This is just another way of saying micromolar, but it's useful when you're mixing tiny little microliters with your tiny little pipette tips. All of these can be directly converted to molarity, but don't forget to convert. Number 6, normality. This one doesn't come up very often, but I mention it because it is sneaky. Normality is expressed with an N, which looks like an M, the measure for molarity. I remember being new in the lab and thinking, well, they probably meant to write an M, but their hand just slipped. No. If molarity measures the number of molecules per volume, then normality measures the number of active molecules. It comes up often in the case of acids. 1 molar hydrochloric acid is equal to 1 normal hydrochloric acid, but 1 molar sulfuric acid is 2 normal because each molecule adds 2 units of acid. So be careful. But honestly, if you're handling acid, you should probably be careful anyway. Number 6, enzyme activity units. When you buy an enzyme, like a restriction enzyme, they don't give you the concentration in normal units. It's hard to measure the true concentration of an enzyme, and companies are lazy and cheap, and so instead they give you the concentration in units, which are determined experimentally based on a measurement of what the enzyme is actually doing. So for example, if your enzyme cuts DNA, they'll go in and measure how much DNA can this cut per minute, and they'll call that however many units. The important thing here is that the unit is defined differently for each enzyme. So the correct number of units will completely depend on the enzyme and the source. For most enzymes, the manufacturer will tell you the right amount to use in standard protocols. Number 7, copy number. Copy number. My favorite, the most beautiful, the most intuitive way of expressing a concentration. For this, we simply say the exact number of molecules for a given volume. 200 plasmids per cell, 100 mRNA molecules per cell. Unfortunately, it becomes impractical for large volumes and the huge numbers of molecules that we use in a typical experiment, but it works great when we shrink down into the world of a single cell. Okay, that's all the ways I can think to express concentration. Keep your measurements straight and your experiments will always work. Until next time, happy concentrating.